QED, also known as Quantum Electrodynamics. What this theory does is that it represents electromagnetism in terms of quantum fields. It also calculates the probability of an interaction occurring, and this is important as this predicts the motion and interactions of not just electromagnetic forces, but also charged particles. Now, just a brief history as to where this came from. The foundations were laid down by Paul Dirac, and what he did was he created an equation that describes the spin and motion of electrons, and in doing so, he combined quantum mechanics and special relativity. The theory was then developed further by three people independently: Feynman, Tomonaga, and Schwinger, and we'll talk about Feynman in just a moment. So, why QED? If we look on the left-hand side here and imagine the scenario of two negatively charged particles coming together, we'd expect them to repel due to the forces that they exert on each other being opposite or opposing each other, as shown by the electric field lines. But if we look on the right here, what the quantum side does is that it breaks down these continuous fields and replaces them with discrete packets, or also known as photons. And so the repulsion is due to the emission and absorption of these photons. Now, Feynman represented equations in diagrams known as Feynman diagrams. And so this example here represents annihilation. So if we zoom into it a bit, what annihilation says is that when an electron and its antiparticle, also known as positron, collide together, they form two photons as shown in the equation. Now, if we look at the time axis here on the left-hand side, and we look where the positron is going, this sort of implies that the positron is going back in time.
There are four main features of a Feynman diagram that can help construct an interaction, and each of those features corresponds to a certain part of an equation describing that interaction. Arrows are used to show the incoming and outgoing particles, with the incoming particle corresponding to the symbol I and the outgoing particle corresponding to the symbol O. A photon is shown as a line in the form of a sine function, or a squiggly line, representing the term minus Ig subscript mu nu over p squared in the equation. A vertex represents the point where particles meet, is shown as a dot and corresponds to the term IE gamma to the power of mu or nu. Take electron scattering as an example. We know an interaction happens, so we can construct a diagram using the features previously discussed. And by looking at the diagram, we can construct an equation corresponding to the interaction between two electrons.
With the example of electron scattering, we can look at Feynman diagrams to visualize some of the possible interactions between the two particles, of which there are infinite, and formulate an equation that can very closely approximate the real solution. We can first look at the most basic interaction of electron scattering. Two electrons move closer together, one emits a photon that is absorbed by the other, and both electrons then recoil in opposite directions, as we would expect from classical mechanics. However, there are many more possibilities of how this interaction might occur. For example, both electrons may separately emit and absorb a photon each, or the photon emitted may split into an electron-positron pair before recoalescing into a photon and being absorbed, or some combination of the above, or any of infinite other possibilities. An electron may emit a photon after the interaction, or it may emit the photon and then absorb the photon that it itself emitted, or this could happen before the interaction of the two electrons. All this means that as to get the exact solution, all of the infinite possibilities must be considered. It is necessary to simplify this and only take into account the most likely paths, to end up with an approximation that is good enough to the exact solution.
The infinite probabilities that we'll have to consider in an event means that there are lots more equations that we'll have to formulate and take into account, making finding the final probability much harder. And this is why we bring out the essential tool for quantum mechanics, the perturbation theory. When the original equation is too complicated to solve, perturbation theory is used to formulate similar equations that are solvable. Although the solutions resulted from this will never be exact, it will provide a relatively satisfying solution. In the case of electron scattering, perturbation theory is used based on the fact that the more complicated the interaction, the less it will contribute to the final probability amplitude. More specifically, each vertex in the Feynman diagram reduces its contribution to the final probability by around a factor of 100. Therefore, as odd-numbered vertices diagrams don't exist, all the 4 vertices diagram will each only contribute 0.01% to the final probability amplitude, and the 6 vertices diagram will only each contribute 0.0001%, etc. This leads to the fact that the most probable interaction for electron scattering is the simple case with 1 photon exchange with its 2 vertices, therefore simplifying the calculation and making the equation solvable. Notice the arrows in these diagrams were omitted for simplicity, as we're only discussing the vertices here. Quantum electrodynamics is a revolutionary contribution to the development of quantum mechanics. With the help of Feynman diagrams, it has revealed the inherent beauty of nature since the 20th century and will keep contributing to our understanding of the world we live in.